Okay, hi everyone. So today we will continue to explore the graphs. So today our topic is minimum spanning tree. So a minimum spanning tree MST is defined as a spanning tree that has the minimum weight among all the possible spanning trees. So the minimum spanning tree has all the properties of a spanning tree with an added constraint of having the minimum possible weights among all possible spanning trees. Like a spanning tree, there can also be many possible MSTs for a graph. So a spanning tree is a tree converted from a graph. So here are the properties of a spanning tree. So the spanning tree holds the below mentioned principles. First, the number of vertices in the graph and the spanning tree is the same. There is a fixed number of edges in the spanning tree, which is equal to 1 less than the total number of vertices, that is E equals to B minus 1. The spanning tree should not be disconnected, as in there should only be a single source of component, not more than that. The spanning tree should be acyclic, which means that there would not be any cycle in the tree. The total cost or weight of the spanning tree is defined as the sum of the edge weights of all the edges of the spanning tree. There can be many possible spanning trees for a graph. So the minimum spanning tree has all the properties of the ordinary spanning tree, like these. And there is a constraint that they have the minimum possible weights among all possible spanning trees. So today we'll first talk about one algorithm to create a minimum spanning tree. So that is called Kruskal's spanning tree algorithm. So this is one of the popular algorithms for finding the minimum spanning tree from a connected undirected graph. So this is a greedy algorithm. The algorithm workflow is as below. First, it sorts all the edges of the graph by their weights. Then it starts the iterations of finding the spanning tree. At each iteration, the algorithm adds the next lowest weight edge one by one, such that the edge picked until now does not form a cycle. Now we'll use this graph to illustrate the process. So this is a very complex graph. So first, we have all the edges in the graph, and then we sort it and store it here. So these are the source, destination, the vertices, and the weight. So they are sorted according to weight in ascending order. So we will just add the edge in the list here accordingly. So you can see the smallest edge has weight 1, that is from 7 to 6. So we will just add these two vertices and this edge. So the second one is weight 2, that is between 8 and 2. So we'll put it here. Then there's another one with weight 2, that is between 6 and 5. So you can see 6 and 5, we already have 6 here, so we will just add 5 to it. Then 0 and 1. So these two are also not connected here, so we just put it here. So they'll be connected to these parts later. Then 2 and 5 are connected with weight 4. Here. Then 8 and 6. But you will see that 8 and 6, if we add an edge here between 8 and 6. So you can see here you will form a cycle. However, according to our algorithm, we will just add the edge such that the edge picked until now does not form a cycle. So we'll not add an edge here, we'll just ignore this edge from the original graph. And because you cannot have a cycle inside your tree, whatever tree it is, your spanning tree will not contain cycles. If they have cycles, it will not be trees. So we'll just ignore this edge, and we'll just look at this between 2 and 3. Then 3 and 4 here with weight 9. And you can find that all the edges are now connected, and you have your minimum spanning tree. So here is the time complexity analysis of this algorithm. So it is OE times log E, or OE times log V. So the first part of our algorithm, the Kruskal algorithm, needs to sort all the edges. So it will take OE log E time. So after sorting, we iterate through all the edges and apply the find union algorithm. We find and union operations can take at most O log V time, because you just need to connect these edges inside your linked list, so it is O log V. So overall complexity is combining these two, so it's E log E plus E log V. So the value of E can be at most OV squared. So O log E and O log E are the same. Therefore, the overall complexity is OE log E. Because these and these are same, so it is like the twice of E log E. And constants are ignored in the big O notation, so it's generally E log E. And here is why we will use a minimum spanning tree. So a minimum spanning tree is the subset of the edges of a connected undirected graph that connects all the vertices together without any cycles and with the minimum possible total edge weight, as we have talked about just in several minutes before. So it is a way to connect all the vertices in a graph in a way that minimizes the total weight of the edges in the tree. So the standard application is to a problem like phone network design. You have a business with several offices. You want these phone lines to connect them with each other, and the phone company charges different amounts of money to connect different pairs of cities. You want a set of lines that connects all your offices with a minimum total cost, and it should be a spanning tree. So since if a network isn't a tree, you can always remove some edges and save your money. So that is the direct application of MST, and it is also used to solve other problems, so we'll perhaps talk about that later. And there's actually another common way, another kind of algorithm to create a minimum spanning tree that is called the prim algorithm. So we'll talk about this algorithm in our next activity. And so today you just need to make sure that you understand this part. So you will just sort them, and you'll make sure that you just add the edges one by one. And if adding one edge will cause a cycle to be formed, you will just ignore this part and keep the adding process on until all the nodes are connected in this graph, and it is a minimum spanning tree. So that's all for today's activity. Thank you.